Classical physics models the universe as a vast, pre-existing physical box. In this framework, human observers are treated as passive inhabitants, tiny points of life trapped inside an unimaginably large container. For centuries, empirical science has operated under this assumption of an objective, independent cosmos, a reality with fixed dimensions, regardless of measurement. Modern physics has since challenged the viability of this external container model. The Kochen-Specker theorem proves that physical properties and spatial coordinates do not possess definite values prior to a measurement interaction. Without an observer to draw a distinction, a system remains a field of unactualized potential. Space, distance, and position are created through the active measurement rather than revealed by it. This suggests that the vastness of the entire cosmos is a property of the observer's own measurement boundary. The geometry of the universe is an emergent readout of the interaction between the observer and the state vector. Reframing the observer as the primary container for space requires a shift in how we define physical scale. In set theory, a simple closed interval, like the distance between the numbers 0 and 1, contains an uncountable infinity of distinct points. This demonstrates that infinite complexity and capacity can be structured entirely through internal division. High-density information does not require expanding the outer walls of a system. Biological systems directly mirror this exact mathematical structure. While the observer has a finite physical size, it handles a continuous high-dimensional flux of information within its sensory boundaries, an internal state space as deep and divisible as the number line. We are modeling a system where structural complexity is held inwardly. The observer functions as a finite boundary that contains an internal, continuous infinity. Differential geometry explains how internal density projects an external horizon. Through stereographic mapping, a finite sphere projects onto a flat, unbounded plane. Every surface point maps to a specific coordinate. As we move toward the top, the projected points stretch toward an infinite distance. The finite sphere represents the internal structure of the observer, while the projected plane represents the boundless physical universe as we perceive it. The Poincaré disk model illustrates why this space feels inescapable. In this hyperbolic geometry, the distance metric scales nonlinearly. Navigating toward the edge causes perceived distance to expand. Reaching the boundary requires infinite time and energy, even though the system remains physically bounded. This proves that a system can occupy a finite volume while rendering a boundless, unreachable spatial reality to the observer within its metric. The necessity of this spatial projection is found in the computational limits of human biology. Perceptual Interface Theory suggests that the raw, unconditioned quantum states of the environment are infinitely dense with information. Attempting to process this raw data would overwhelm our biological systems. Evolution solved this by implementing a rigorous data compression format. We experience three-dimensional space and linear time as a biological graphical user interface. This format allows us to navigate the environment without having to calculate the underlying complexity of the quantum plenum. Physical objects and cosmic distances act as low-dimensional icons. They are functional simplifications that allow us to interact with high-density data. Through this interface, telescopes simply allow us to resolve infinite internal depth of our own state space. Observing a distant galaxy is the cosmic equivalent of zooming in on a nested folder. We are accessing high-resolution information stored within the observer's own architectural boundaries. The human observer functions as the localized boundary that resolves unconditional potential into the structured, non-repeating reality we call the universe.